Hello everybody, and welcome to this second video about organic chemistry for A-level chemistry. And in this video we're going to be looking at nomenclature, which is all about how you name organic compounds. And in this video we will be looking at the rules that there are for naming. We'll be looking at how you name organic compounds when you've been given a formula, whether that's displayed formula, structural or skeletal formula. And last of all, we'll look at how you draw structures when you have been given a name for an organic compound. Now, what I should say is that I'm going to be focusing on the functional groups and families of organic compounds that you're most likely to encounter in Year 1 chemistry. I will do another video for Year 2 nomenclature and isomerism sometime in the near future. Organic compounds are named using the International Union of Pure and Applied Chemistry System, or IUPAC for short. To reassure you, you don't need to remember what IUPAC stands for. You just need to be able to use the naming rules that I'm going to outline now. Now, the IUPAC rules for naming chemicals can seem quite complicated, so I'm going to try and break down the structure that these names can have. First of all of the names have got a root. Now this root, which is sometimes called an infix, but normally it's called a root. Now this tells us about the length of the longest unbranched hydrocarbon chain present in a molecule. And for simple molecules, this will actually be how the name of the molecule begins. Now the good news is that the longest unbranched hydrocarbon chain that you're going to encounter is going to be 6 at A-level chemistry, whichever course it is that you're studying. So you only need to learn the root word for these 6. And you will have come across these before, hopefully at GCSE you'll remember this. And so if there is 1, it is meth, and 2, it is eth or eth, and then it becomes prop, bute. And those are the 4 that don't kind of make sense, so to speak. You just have to remember those 4. And then after that, it becomes like the number of sides of a particular shape. So it becomes pent for 5 and hex for 6. So those are the root parts of the name. Meth, eth, prop, bute, pent, hex. I recommend learning those as a matter of some importance. Now then we have got the particular ending. Now the ending for simple molecules will be either something like ane, for if there are no double bonds, or it might be ene if there is a double bond present. And so a simple molecule might have a name such as methane or ethene. More complicated molecules might also have a suffix. Now a suffix is a part of a word that goes at the end of a particular word, and this suffix actually changes the name ending depending on what particular functional group might be present. Now an example of that is, say, an alcohol, and the name ending will change to ol. And last of all, and this is not always the case that we have one of these in a molecule, but that is a prefix. Now pre meaning before, and so this will come in at the start. And prefixes, like I say, you don't have prefixes for all molecules, but this prefixes tells us about any branching that is in the organic compound, but it also tells us about certain functional groups that might be sticking off the main carbon chain. So let's just have a quick recap. We will have a root part of the name, which tells us how many carbon atoms there are in the longest unbranched carbon chain. And then there'll be a typical ending, which might be ane or it might be ene. And then there will occasionally be a suffix, which will be where that ane or ene gets changed slightly if the functional group is more complicated, and there will also sometimes be a prefix indicating branching or additional functional groups aside from the main one. I think the best way to learn nomenclature in greatest depth is actually through exposure to a variety of different organic compounds. And so what I'm going to do is I'm going to work through the organic compounds that you're going to encounter in Year 1 chemistry. I'll start with the ones that you'll encounter most frequently, and I'll build up into other ones that become more complicated, and I'll introduce some of the IUPAC rules as we go on through. So let's start with alkanes, which are the family of chemicals that you will have encountered at GCSE, and they all have got the name that ends in the suffix -ane. Now, alkanes are quite straightforward, so we won't spend long here. Let's just explore. Here we've got one carbon, and therefore the root for this word is going to be meth. And so, since we have got one carbon and it is an alkane, the name will be just simply methane. We always run the root and the name ending together. Now for this one, we've got 1, 2, 3 carbon atoms in our longest chain, and therefore the root is prop, and since it is an alkane, we just call it propane. Moving on to look at alkenes now, we'll start with a few simple alkenes. What these all have in common is the name ending -ene. So if we have a look at these 4 alkenes, first of all, we've got the one here top left, where we have got 2 carbon atoms, and so this will have the root eth, and because it's an alkene, we call it ethene. This second one here, top right, this one has obviously got 3 carbons, and so because it's got 3 carbons, it gets the root prop, and so it becomes propene. Now, alkenes are a little bit more complicated than alkanes, because what about these 2 here at the bottom? So we've got this bottom left, which has got 4 carbons, which therefore means it gets the root bute, and then this bottom right one has also got 4 carbons, and it also therefore must have the prefix bute. So we've got 2 alkenes that are called bute, and they do both get called butene. However, the root and the suffix are separated this time by a number, and this number indicates the position of that double bond. And what we do here is we number the carbon atoms. We start at one end of the chain and we number them all. 1, 2, 3, 4. And so this alkene, the double bond, is considered to be on position number 1. It's between the first and the second carbon, so we say that the alkene is attached to the first carbon because one of the IUPAC rules is that we keep our numbers as small as possible. And so this alkene is called but1-ene. What we've got in the second alkene that looks like it should be called the same thing is we've got our double bond between the second and the third carbon in the chain. And so, because it's between the second and the third carbon, and because we have got the rule that we must keep the numbers as small as possible, we call this but2-ene. Just a quick word about numbering. You can number from whichever end of the chain gives you the smallest numbers. It is not a case of always numbering from left to right or right to left. The rules are quite strict on which functional groups always should have the lowest number, but if you've got something simple like an alkene, the rule states that the number must always be as small as it could possibly be. So for instance, the but1-ene could alternatively, if you'd numbered from the right moving to the left, you could argue that it is on the third or between the third and the fourth carbon atom, and so it could be called but3-ene, but because the rule says that we keep the numbers as small as possible, we were right to number them in the direction that we did at first, and but1-ene has got the smaller number. Let's take a look at some more complicated organic compounds. These are going to have alkyl groups acting as branches. So what that means is you've got the main part of a carbon chain, and then you've got another carbon chain sticking out part way along. And so an alkyl group is often represented as an R, where that means we've got a carbon chain of any length, and the branch is considered to be any carbon chain that is moving off the main longest carbon chain. And so the rules for naming these carbon chains are dependent once again on the number of carbon atoms in the R group. And so the R group length, I think you're going to be limited to 1, 2 or 3, but I'll include 4 in there as well. And so they have the same naming format as the root part of the main part of an organic compound, but the end of it changes slightly. So an alkyl group of only 1 carbon is called a methyl group. If there are 2 carbons in the chain, it's referred to as an ethyl group. 3 carbons would be called a propyl group. 4 carbons would be a butyl group. So if we take a look now at these 3 examples, the first thing that we must always do when trying to name an organic compound is finding out what the longest part of the chain is. Now in this one, we've got 2 choices here. We've got this group, which is a chain of 3. Alternatively, we've got this group on here, which actually is also a chain of 3. And so let's stick with our green bit as being our longest carbon chain. And so what we've got part way along is we've got 1, 2, 3 carbons in our chain. So the root is going to be prop. There are no double bonds, so it's going to be propane. But what we've got this time is we've got an extra carbon sticking out part way along the chain. There is only 1 carbon in this alkyl group, and so we call it methyl propane. And successive words are actually merged together. So methyl propane is actually technically only 1 word. Finally, as part of this name, we sometimes need to indicate the position of the alkyl group. Now for us, the alkyl group is on the 2nd carbon, whichever end you start counting from, and so this could be called 2-methyl propane. And that 2 would be separated from the methyl propane by a hyphen. However, on this occasion, this is not necessary because the methyl group could not be on position number 1 or 3 with the molecule still retaining the name propane, because if it was on position number 1, the carbon chain would be extending down here and it wouldn't in fact be propane anymore, it would be butane. And so as such, the name, if this was an exam and this was the mark scheme, the number would probably be in brackets, implying that it's non-essential for naming of this compound. If we move on to the one at the bottom here, we need to find the longest carbon chain. So the longest carbon chain could be like that, which would be a chain of 5. Alternatively, it could start at the end and then bend down towards the bottom, as I've shown here in the yellow. But this would also be a chain of 5, so it doesn't really matter whether you consider the horizontal green or the yellow that turns a corner. It doesn't make any difference to our naming. I'm going to consider the green highlighted region to be the main longest unbranched chain. So 1, 2, 3, 4, 5. I've numbered my carbon atoms. It's the same in either direction. And so we've got 5 carbons, which means that is pent. There are no double bonds, so it is pentane. We do now have an alkyl group sticking out. This has got 2 carbon atoms in it, which means it is ethyl. So we've got ethyl pentane. The carbon atoms are in position number 3, and so this is 3-ethyl pentane. And again, actually, if it was in position number 2 or position number 1, it wouldn't be pentane anymore, and so arguably that 3 is not vital, but it is helpful for a speedy assignment of structure. Last of all, top right, we have got a chain of 1, 2, 3, 4, 5 as we go along here. Or we've got a chain 1, 2, 3, 4, 5, 6, chain of 6 as we go that way. Whoops-a-daisy, it looks like we've got a couple of atoms of hydrogen missing. And because 6 is bigger than 5, of course, we go 1, 2, 3, 4, 5, 6. We need to number these round the corner, so to speak, because that is the longest unbranched chain of carbon atoms. Now, I chose to number from the left, not because that's what I've always been doing, but actually because that's where my alkene is. And alkenes have got a higher priority for naming than our alkyl groups. And so this is a chain of 6, so it is hex. It is an alkene, so it is ene. The alkene double bond is between the first and the second carbon atom, so it becomes hex 1-ene. We've got a methyl group sticking out of the 4th carbon. And so this becomes 4, because it's on the 4th carbon, methyl hex 1-ene. Not forgetting that we need hyphens to separate a number from letters, and we have that for the prefix. We also have it to separate the root from the suffix when there's some variety about where that functional group might be in a molecule. Let's take a look now at situations where there are 2 or even more alkyl branches coming out of the longest main carbon chain. So let's work through these 4. You can pause it and have a go yourself if you're feeling confident, or you can work through them with me. The first one that we've got here, finding the longest carbon chain. I think I've drawn these reasonably straightforwardly. And so we've got a chain of 5. We could have that as well if we moved to the middle and went down. That's still a chain of 5, so that means that's not going to affect our numbering system. So let's start our numbers. 1, 2, 3, 4, 5. So we've got those as our main chain. So that's pent, and that's an alkane because there's no double bond, so it's going to end in ane. This time though, we've got 2 branches. We've got a chain of 1 sticking out and a chain of 2 sticking out. So we've got an ethyl group, that's what a chain of 2 is, and then we've got a methyl group as well. The ethyl group is sticking out of position number 3, the methyl group position number 2. So when we run these 2 together to form part of the main name, there is one extra rule. The rule is the groups are named in increasing alphabetical order. So ethyl begins with an E, and that's closer to the beginning of the alphabet than a methyl group. And so what that means is we're going to call this ethyl methyl pentane. And because we've got some elements of position, the ethyl group is on position number 3, and so this is 3 ethyl, 2 methyl pentane. Notice there the hyphens separating the numbers from the letter L and the letter M here, and the number from the letter E. So 3 methyl, 2 ethyl pentane. If we move on to the next one, we've got a chain of 1, 2, 3, 4, because that turns around the corner. So this is going to be bute. It's an alkene, so it is butene. We're going to need to number our carbon atoms. 1, 2, 3, 4. And that means that our alkene is going to be called bute2-ene because the double bond is between the 2nd and the 3rd carbon in the chain. And then if we consider alkyl groups sticking out of the side, we've got one here and we've got a second one here. So we've got 2 groups that are in fact both methyl groups. And this introduces an extra element to the naming. If we've got 2 of the same, then we add the prefix di to the name of the alkyl group. And so what this is going to be is this is going to be dimethyl bute2-ene. But since the methyl groups could actually be in a variety of different positions, we need to indicate with a 2 and followed by a comma and then a 3, the fact that these two methyl groups are on the second and third carbons. If we move on to take a look at the compound that is bottom left, looking for the longest carbon chain, 1, 2, 3, 4, 5, that's a chain of 5, which you can't get if you move around in any bendings up or down. So that is a chain of 5, which gives us pent. We've got an alkene again, and so we've got 1, 2, 3, 4, 5. And so this might make you think it should be pent 4-ene or pent 5-ene. However, we must use the numberings that gives us the lowest numbers overall for our functional group for the alkene. And so it's not numbering left to right, it's numbering right to left. And so this gives us the name pent 1-ene. Clearly that can't be the end of it though, because we've got these different alkyl groups sticking out of the side. We've got a methyl group and a methyl group and a methyl group and a methyl group. In fact, they're not different, they're all the same. We've got 4 methyl groups. And so we need to acknowledge that by calling this methyl pent 1-ene, but it's not just methyl or dimethyl or even trimethyl. This is tetramethyl, tetra meaning 4. And so, if we've got 3 of the same, it would be called tri. 4 of the same is tetra. And so we've got 4 methyl groups sticking out of our pent 1-ene in various positions. What are the positions? Well, we've got 2 of them on the 3rd carbon atom in the chain, and we've got another 2 on the 4th. And so this becomes 3, 3, 4, 4 tetramethyl pent 1-ene. And in a similar way to the alphabetical order, we need to start at the smallest numbers for the positions of the branchings. So it's 3, 3, 4, 4 tetramethyl pent 1-ene as opposed to 4, 4, 3, 3 or any random jumblings. We start with the smaller numbers first. Now if we have a look at the group bottom right, we've got 1, 2, 3, 4, 5, 6. That's the chain of 6. I think that's the smallest chain that we've got. We've got another chain of 6 if you start at the top and go down and then right, but I'm just going to keep it with our horizontal ones for now. And so it's a chain of 6, so it's going to be hex. There are no double bonds, so it's in fact nice and easily going to be hexane. This time let's have a look at our groups. We've got a methyl group here and a methyl group here. And then we've got an ethyl group in the middle. And so ethyl, methyl, and methyl. So in terms of numbering, we've got 1, 2, 3, 4, 5, 6. That gives us the numbers 2, 5, and 4. Alternatively, we could number from the other end, and that gives us a 2, a 3, a 5, as our branching numbers. So we've either got 2, 3, 5 or 2, 4, 5. Okay, so the green numbers are the ones to go with because that gives us the smallest numbers overall for the carbon chains, and there's no double bond to consider. So it's going to be dimethyl because there are 2 methyl groups and there's only 1 ethyl. In terms of alphabetical order, we don't consider the di, tri, or tetra in the alphabetical order. We only consider the E for the ethyl and the M for the methyl. So even though D's before E, this is going to be ethyl dimethyl hexane. We do need to consider the numbers. The methyl groups are on position number 2 and position number 5. So this is going to be 2, 5, and then hyphens again. And the ethyl group is on position number 3. So this is 3-ethyl, 2,5-dimethyl hexane. Let's move on now and have a look at the halogenoalkane family. Halogenoalkanes have got the functional group Rx, where X is a halogen that is covalently bonded to a carbon chain. Now halogens, group 7 this is, have obviously all got different names, and so when it comes to naming them as part of an organic compound, the prefix that we use must also change as well. And so bromine as a halogen will have the prefix bromo. Chlorine has got the prefix chloro. Fluorine has got the prefix fluoro, and iodine has got the prefix iodo. And so the halogen is never considered to be part of the main functional group. The halogen is always considered to be a prefix. And just to remind you from the previous page, if there's more than one of the same halogen, we're going to use the extra phrase di or tri or tetra, depending on how many there are. If we look at these 4 different halogenoalkanes, starting with the one on the top left, we have 1 carbon atom, so this is going to be meth. There are no double bonds, so it should be methane. What there is are these 4 chlorines, so this is going to be tetrachloromethane. No need for any numbers because those 4 chlorines could not be in any other position. If we move on to the second one, we've got a chain of 2. So we've got 2 carbon atoms, so this is going to be ethane. Again, no double bonds. We've got 2 chlorines this time, so this is going to be dichloro. We have got carbon number 1 and carbon number 2, so this is going to be 1, 2 hyphen dichloro ethane. And dichloroethane, remember, is all one word. If we move on to our third example, we've got a chain of 4, so it's going to be butane, no double bonds, so butane. We have got 1, 2, 3, 4, or alternatively 1, 2, 3, 4. Obviously the green, if we use them for our locants, our positioning, we're going to end up with smaller numbers. So this is going to be bromine on position number 1. So this is 1 bromo. Chlorine is on position number 2. So 2 chloro, butane on there. This bottom example is slightly different, or at least it introduces an extra level of complication, because what we've got is we've got our 2 options for how we number them. 1, 2, 3, 4 from the left, or 1, 2, 3, 4 from the right. It's very clear that we've got 2 fluorine groups, so this is going to be difluoro, and we've got 2 iodine groups, so this is going to be diiodo, and it's also clear that we've got butane because it's a chain of 4. What's not clear is which of these numberings do we use? Do we use 1, 2 difluoro, 3, 4 diiodo, or do we use the red numbers? And the answer for this is we use the numbers that give highest precedence to the halogen that's further towards the front of the alphabet. And so, since F comes before I, this is going to be difluoro as higher precedence, and then diiodo as second, which means that we're going to number it in that sequence too. So we're going to use our 1, 2 difluoro and our 3, 4 diiodo. And the reason this is an issue is if we'd used the red numbers, the total of all of our numbers would have been exactly the same. We'd have used 1, 2, 3, 4 once, whichever sequence we use. But as I say, what's really important to remember is we need to give higher precedence to F before I. It's complicated because there's no different functional group. They're both halogens, but F before I. It's very rare that you get that situation, and frankly, I suspect you wouldn't get something as ambiguous as that for A-level chemistry. Let's have a look next at alcohols, which have got the functional group OH attached to an alkyl group of some sort, and they will always have the suffix of -ol as the name ending. Let's have a look at naming these alcohols that we've got drawn here. First of all, top left, we've got 1 carbon atom in this chain, and so we've got meth for that root, and then in this instance it becomes methan because methane is very similar to methane, but there's just an OH group instead of one of the hydrogens, so we just in fact call this methanol, with the 1 carbon giving us in fact on this occasion methan. If we have a look at the second one in the middle, we've got 3 carbon atoms in this chain, and so this is going to be propan, and it's going to be ol because we've got the alcohol. And similarly to our alkenes, we need to give a position to the OH group on this occasion, because the OH group for the alcohol could be on the end or it could be in the middle. And so on this occasion, the alcohol group is in the middle on carbon atom number 2. If you have a look, 1, 2, 3, it's on carbon number 2. If we start numbering on the top right, we'll start numbering from the right hand side, 1, 2, 3. And so this is also going to be propanol, but we need a different locant. We need the number 1 for it to be propan-1-ol. Having a look at the one on the bottom, we've got a chain of 4, and we've got this OH group. So this is going to be butanol, butan for the root. And we've also got, on this occasion, we've got a methyl group sticking out on here. And so we've got 2 different options. We could have 1, 2, 3, 4, or we could have 1, 2, 3, 4. And on this occasion, the yellow numbering system is going to win, and the green won't be used. And the reason for this is we always give the functional group the lowest number that we can if there is an option. And so on this occasion, this is going to be butan-2-ol because the alcohol is located on the second carbon. And so the methyl group, this is going to be methyl butan-2-ol. The methyl group is located on carbon atom number 3. So this would be 3-methyl butan-2-ol. Next, we're going to take a look at aldehydes and ketones. I'm going to consider these two together because they're both quite similar, and actually their naming conventions are very, very simple. There's not that much variety to the types of questions that you could be asked. Let's take a look at aldehydes first, which have got the functional group C double bond O with a hydrogen attached to the same carbon with the oxygen doubly bonded to the carbon. And then we've got R for some alkyl group that could be really, really long, or it could even just be a hydrogen. So in our first example, we've got a carbon chain of 2, and then we've got the aldehyde functional group at the end. So we've got ethan as our root for 2 carbon atoms, and then the name ending for aldehydes, very easy, just ends in al for aldehyde. If we take a look at the bottom one, we've got a chain of 4, so this will be butan, and then again al. So butan is for 4, al is for aldehyde. This time we have got a methyl group on position number 2. We always number from the aldehyde end first, 1, 2, 3, 4, and so this is going to be 2-methyl butanal. If we take a look at ketones now, which are very similar to aldehydes, they've still got that C double bond O group, but this time it's in the middle of a chain. So we've got an alkyl group going one way and an alkyl group going the other way. And on this occasion, they cannot be hydrogen atoms. If one of these was a hydrogen atom, this would be an aldehyde. And so the smallest ketone that we can actually have is the first one that we've got here, which is 3 carbon atoms in a chain with the double bond oxygen in the middle. So this is propan, because we've got 3 carbon atoms in the chain, and ketones just have a name ending -one. So propan for 3, -one, propanone. No number needed, because if that double bond was not in the middle, it wouldn't be a ketone anymore. It would be an aldehyde, propanal. For the bottom one, we've got 5 carbon atoms in a chain, so this is pentan for 5. The ketone takes higher priority over the methyl group that we've got, because you'll notice we've got a methyl group here. So we number from the end closest to the ketone, 1, 2, 3, 4, 5. So this becomes pentan-2-one, in the same way as alcohols and alkenes. So this is pentan-2-one, but of course we've got that methyl group, and so this is 4-methyl pentan-2-one. Let's take a look now at carboxylic acids. which are characterised as having the functional group C double bond OH with an alkyl group attached here, although that could be a hydrogen. Now the suffix used for carboxylic acids is always the same, and it is always oic acid, which seems funny, but the name ending is always nice and predictable, and in fact I think carboxylic acids might even be the easiest to name. So here we've got a chain of 1, and so that is going to be methan as the root, and then we just add the suffix on at the end and it becomes methanoic acid. Methan for the root of 1 and oic acid. Moving on to the second one, we have a chain of 2, so this becomes ethan for 2, and then oic acid for the carboxylic acid. At the bottom, we've got a chain of 3, so propan is our root, and our end is going to be oic acid on here. I say carboxylic acids are the easiest. That's because the functional group has to be on the end in a similar way to aldehydes. So there's never any position, no locant needed for the functional group. What we do need on this occasion at the bottom, though, is we do need a location for our chlorine group. So the functional group always gets given position number 1, which means that the chlorine is put into position number 2. So this becomes 2-chloropropanoic acid, and the chloropropanoic acid is technically all one word. So that was the end of carboxylic acids. There really was that little to it. Moving on to amines that are about as difficult, really, and the amines are characterised as having the functional group NH2 attached to a carbon chain of some sort, and they're given the name ending amine, a very, very logical suffix indeed. So if we try and name these 3 molecules that are here, we have got a chain of 1. So this is, on this occasion, referred to as a methyl group. And so this is called methyl amines. And so that's probably the hardest part of naming amines, is that the carbon chain, the R group, is almost named as if it was a branch to the amine itself. So the second one, where we've got 2 carbon atoms in this R group, would be referred to as ethyl amine. The third one at the bottom, a little bit more complicated, but not much. We've got a methyl group here, and we've got another methyl group here. And so where we have got 2 methyl groups, just like before, we refer to this as dimethyl. And then this has still got the functional group of an amine, even though there's an extra hydrogen that has been replaced. So this is referred to as dimethyl amine. The last functional group that you're likely to come across in Year 1 A-level chemistry is the nitrile family. And the nitriles have got the functional group where you've got a carbon that is triply bonded to a nitrogen atom, and then you've got another carbon chain of any length. And the suffix used here is very, very logical, just like before. This is called nitrile. That's the name ending of any nitrile. If we take a look at how to name these nitriles, just as before, we look for the longest carbon chain that's unbranched, and we've got 3 here. So this is actually referred to as propane. And then we've got our nitrile functional group. So this is just simply propane nitrile. The second one, we've got a chain of 2. So this is ethane, and again it's nitrile, so it's ethane nitrile. So at first glance, the most difficult thing about nitriles is actually that their name is incredibly literal. There is a propane attached to a nitrile, or there is an ethane attached to a nitrile. Where it gets a little bit complicated is with branching, but it still follows the same rules as before. So we've got a chain of 4. So this is butane nitrile. And we've got 2 different branches this time. We've got a methyl branch, and we've got an iodo branch. And so they need to have locations. The carbon here with the nitrile on it is position number 1. Then that's position number 2, and then iodine's 3, and the other carbon is 4. It's really important to know that you do include the carbon that is attached to the nitrogen in terms of the numbering. And so we always list these alphabetically, and I comes before M in the alphabet. So this is iodo methyl butane nitrile. The iodo group is on the third carbon and the methyl group is on the second. So this is 3-iodo, 2-methyl butane nitrile. While nitriles are not that complicated to name, it does give us an opportunity to discuss the separation of the root and the suffix. And there is a slightly peculiar seeming rule at first, which is that you can't have two consonants next to each other at the connection between the root and the suffix. So what you couldn't have is you couldn't have butan nitrile. And so this becomes butane nitrile, and that E will often be in bold on a mark scheme as a complete non-negotiable. And so, as I say, one of the IUPAC naming conventions is you cannot have two consonants next to each other connecting the root and the suffix. And similarly, you couldn't have two vowels next to each other. You would need to drop one of the vowels as you connect the suffix and the root together. I'll give you an example of that in a minute. A good platform to explore those extra naming conventions is to look at situations when there's more than one functional group. When this is the case, you need to look at what's called the order of precedence. And so the group which has got the highest precedence, or highest priority it's sometimes called, forms the suffix, in other words, the name ending. All the others are considered then to be as kind of branches, they're sticking out from the main molecule, and they get given prefixes. Let's take a look at the 6 functional groups you are most likely to encounter in Year 1 chemistry in their precedence order. And so first of all, the thing that takes greatest precedence over any of the others is the carboxylic acid functional group, which means that there is almost no chance that this will be considered to be anything other than the main functional group. And so usually you're going to use the suffix, which is oic acid. A prefix does exist for it, but I'm going to put it in brackets because I can't consider this very likely that it will come up. But the prefix would be carboxy, if that carboxylic acid group was considered to be a branch. Second on the precedence list is the nitriles, and this is a good opportunity to recap all the suffixes. The nitriles ends in nitrile for its name, and in fact if we just have a recap of the suffixes, aldehydes is next on the priorities, and that's got al as its suffix. Ketone is next, and that ends in -one. Then we've got the alcohols, which is ol, and amines, which is amine as its suffix. The prefix for the nitrile, it's quite unlikely that you're going to use this one as well, I suspect, and cyano is the prefix because nitrile's got a lot of the same elements in it as cyanide. Aldehydes would be formyl, again putting that in brackets because I think that's unlikely. Oxo for a ketone functional group as considered to be a branch, maybe, or not necessarily a branch but as a secondary functional group. And then moving on to the ones that I think are far more likely are hydroxy for alcohol groups, and you'd probably use that in biology. And another one that you'd definitely use in biology would be considering the amine to be a secondary functional group of lower precedence, and that would be considered to be an amino group, and would use the amino prefix. And just to remind you again that when you're numbering parts of a molecule, you always give the lowest number to the functional group part. And so the amine would get the lowest number, or the carboxylic acid would get the lowest number if there was one of them present. And so just as an example, if we had an amine and a carboxylic acid, here's our carboxylic acid that I'm going to draw. I'm going to make this ethanoic acid, but there's going to be an amine group at the end. And so what you must always do is you must always look for the group with the highest precedence. And so the group with the highest precedence is this carboxylic acid group. And so this is ethanoic acid. There is this second functional group over here, which is an amine, but you can see the amine is right down there in 6th position in the functional groups, and so this is referred to as aminoethanoic acid. No number needed here because the amino group could not be on that carbon because the carbon has already got 4 covalent bonds and there isn't space for the amino group to be on there. So there's actually no numbering necessary for that amino group. If we look now at a few more examples where there's more than one functional group, in fact there's going to be 2 in every single one of these. If we have a look at the top left, we can see that we've got our chain of 3. We can recognise that we have got 2 functional groups. We've got the nitrile functional group and we've got the alcohol functional group. Of those, the nitrile functional group takes precedence, and so we've got our chain of 3 and it's a nitrile, so this is going to be propane nitrile. But we've got an alcohol group on position number 2, that's number 1, and that is position number 2. So this becomes 2-hydroxy propane nitrile. Top left, we've got a chain of 4. We've got 2 functional groups again. We've got the amino functional group and we've got the alcohol functional group. On this occasion, the alcohol takes precedence, and so the amino is considered to be a branch. As I've said before, you always aim to give the smaller number to the higher precedence functional group. So on this occasion, the alcohol is the higher precedence, and so this becomes butan-2-ol as the higher precedence part of the molecule. Then we've got an amino group, so this is aminobutan-2-ol. We need to locate it, and so the number that is given to locate it is the 4 for 4-aminobutan-2-ol. Looking bottom left now, we've got our chain of 2. We've got 2 functional groups again. We've got the aldehyde functional group and we've got the amino functional group. Aldehyde takes precedence over the amino group, so our chain of 2 makes it ethan, and it's an aldehyde, so it's ethanal. The amino group is the branch, and the amino group is on position number 2, although arguably it couldn't be on position number 1 and still having it being an aldehyde, so 2-aminoethanal or just aminoethanal. If we have a look at the bottom right, we can see that we've got a double bond and we've got the OH group of an alcohol. Now, alkenes don't get given precedence in the same way as the others. Alkenes are often just woven into the name of the molecule. But we've got this, which would be ethene, and we've got the other group that would be ol for the alcohol. And so we could be forgiven for naming this ethene-ol, but this is another example of the IUPAC rules where you cannot have the root part of a name and the suffix both having a vowel, one at its end and one at the beginning. So we can't run these 2 vowels together. So we drop the E from ethene and we run those together and it becomes ethene-ol. So we've lost that E. And that's in the same way as the propane nitrile. We couldn't have those 2 N's next to each other as propan nitrile. It needs to be propane nitrile. Similar, but the opposite way around. We have to drop the E to make sure that those 2 vowels aren't next to each other. Last of all, in our naming rules exploration, let's take a look at situations where organic compounds might have 2 of the same functional groups. These are less likely to come up in Year 1 chemistry. Probably they're likely to be Year 2 chemistry instead. But let's have a look at them now, then we can always be ready for when it comes up in Year 2. And so the 3 families that you're likely to come across are diols, dienes, and dicarboxylic acids. So if we take a look at the diols first, it's very logical that this would be called a diol because there is not 1 alcohol group, but there are 2 alcohol groups in this molecule. We name them in the way that you might expect. We've got a carbon chain of 2, so this is going to be ethane, and then we've got the diols. They're on carbon number 1 and carbon number 2, so this becomes ethane 1,2-diol. Note again, I know they're separated by some numbers, so it's not really obvious that we've got that E in there. When you name alcohols, normally it would be propanol or propan-1-ol, ethanol, etc. But diols need this E in there, definitely needed. And the reason is that if it wasn't there, and we ignore the numbers momentarily, we'd have the N and the D next to each other, and these need to be separated with recognisable by having not one double bond but two, hence diene. When we name them, we approach it in the same way. We've got a carbon chain of 4, so this would be butene, but it's not butene, it is butadiene, and how we name that. So once again, we can't have it as being butadiene because that would give us a T and the D next to each other. So this is going to be butadiene. More than that, of course, we need to have the numberings to give us our locations. So our carbon atoms 1, 2, 3, 4. This becomes buta 1, 3 diene because the alkenes are located on the first and the third carbon atoms in the chain. And so we need that A once again in the same way that we needed the E earlier on. So diols always have that E separating the root and the suffix, and dienes always have the A separating the root and the suffix on here. Last of all, if we take a look at carboxylic acids, where there are 2 carboxylic acids in one molecule, and so we've got one at the end on the left and we've got another one at the end on the right. The longest carbon chain is a chain of 3, and so this would be propanoic acid, but actually because there are 2 functional groups it becomes propane dioic acid on here. So we need the E because once again it would be an N and a D connected by the connected together, and we can't have that. We need the E to separate the 2 consonants, and it's dioic acid because there are 2 carboxylic acid groups. So propane dioic acid, and once again, as I've been saying before, on an exam the E in there would be in bold because it is absolutely essential. Now we've been doing a lot of naming of substances from their displayed formula. Keep in mind that you might be given structural formula or even skeletal formula for some of these substances. So you might need to be able to name something that is a little bit more hidden about its structure. What we're going to finish with in this video is doing it in the other direction, being given the name for the substance and then giving a formula for it from that name. I'm going to be generous and I'm going to make it so that I want you to give displayed formulae. You can always mix it up a little bit if you prefer to give skeletal formulae for speed. I certainly think it's faster, but you decide what you want to do. So I'm going to pop up some names. You can pause it and see if you can try and draw those structures from those names. Okay, so over to you with these. Hopefully you've had a go at drawing those structures. I'll just pop them all up all at once for all 4 of these. Okay, here we go with the answers now for these 4. Just be a little bit harsh with yourself if you've been drawing some bonds that are a little bit sloppy. I think mine are generally okay, but it's really easy to kind of, when you're drawing these, to sort of miss and to have a carbon pointing kind of nowhere and a hydrogen not actually quite connected to it. So really make sure your bonds connect the atoms that they're meant to be connecting on there, and you haven't been sloppy, so do be harsh with yourself at this point. What you shouldn't be harsh with yourself about though is if you've drawn these molecules the other way around. So this OH group could just as easily be up here in this position or this position, provided it's on carbon number 1. Or alternatively, what you could do is you could almost flip this whole molecule all the way around, and so the OH group could be on this end and the bromine groups could be here and here. In the same way, the chlorine and the iodine have to be on position number 1 and then position number 2 for the iodine, then the chlorine, but there's no reason why the iodine couldn't have been at this end and the chlorine here, okay, provided the iodine is on an end and the chlorine is just next to it. Last of all, let's just take a look at 2 complicated examples that has got more than one functional group to them. So again, pause it, try and name these. I'm just going to pop these answers up now both together. And so the top left is butanoic acid, is its main highest precedence carbon chain. So there's a chain of 4, butanoic acid. There is an alcohol second functional group here connected to carbon, not carbon number 1, but it's on carbon number 3. So 3-hydroxybutanoic acid. And last of all, bottom right, we've got a chain of 4 and it's a ketone. So it's butanone would be its normal naming, no number needed. But because we've got a chloro group on this molecule, we do need to call it butanone with a number. So it becomes butan-2-one because it's carbon number 1, carbon number 2. Because the highest precedence goes to the main functional group, and then the chlorine becomes 3-chloro. Okay, that's where I want to end this video. Thanks very much for listening. I'm going to follow this up with a video about isomerism later in the week, so stay tuned for that. Hope it's been useful. Bye-bye.